Hey, hi everybody, and welcome to this Royal Meteorological Society meeting on understanding the weather and climate context of 2023. So delighted you're able to join us. I just have a few administration slides that I'd like to go through first before we get into inviting our speakers. So I'm Liz Bentley, Chief Executive at the Royal Met Society, and we have for a number of years put on a meeting called Understanding the Climate of the previous year. And we have restructured this meeting a little bit and changed the timing of it as well during the year, but it pretty much is an opportunity for us to look back on what happened last year in the context of weather, climate. We'll be looking at sea levels, we'll be thinking about phenology, looking at some of the extreme events that happened last year as well. So a real mixture of talks and a panel of experts to present those as well. So if we just move on to the next slide, just a bit of admin. So obviously we're running the meeting on Zoom. There'll be an opportunity at the end of each presentation to ask questions for the speaker. Please do put your questions in the Q&A tab, not the chat, but the Q&A box. There's the opportunity to vote for a question in there. So if you like the question that somebody else has asked, if you click on the thumbs up that you can see right at the bottom of this slide, then it starts to kind of tally up the questions that are liked, and it will order them so that those with the most votes go to the top, and I can probably address those before the others. So please do put your questions in or vote for other questions that you like within the Q&A, and we'll get through as many of those as we can at the end of each presentation. Zoom itself, if you want to just make the screen a little bit bigger, so you can see the slides that are being presented, then close down things like the chat, and you can also enlarge the screen so you just see the PowerPoint itself. And if you have any technical issues at all, so you get a drop off in sound or something, then I would suggest that you leave the Zoom meeting and rejoin using one of the recommended browsers that you can see listed here, but hopefully everything will be fine. Okay, so just a few things about the society, just just to make you aware of. So the first thing to talk about is our Met Matters. So this is our public outreach arm of the Royal Meteorological Society. If you go onto the RMET's website, there's a tab at the top called Met Matters, and you can click on there, and it takes you through to lots of different content on weather and climate, written really for a general public audience. So giving you information to lots of different things that has been going on around the world, current stories that exist, events and meetings that you may be interested in as well. And now we're just going to run a very short video. It lasts about 1 minute and just gives you a flavour about the membership at the Royal Met Society.
So many conversations start with the weather, and so many answers are yet to be found. But it's when you make a connection, a physical connection, a scientific connection, a connection of interest, that's when the world can change and doors can open. Weather doesn't discriminate, and neither do we. There's been no greater time to unite in our passion for understanding weather and climate and shaping the future of our world for the benefit of science and humanity. We may be over 170 years old, but we are not standing still. Our journals showcase the latest advances whilst drawing on the past, and our members are some of the most forward-thinking people on the planet. We are an independent voice uniting communities. We connect students with mentors, climate scientists with ecologists, communicators with researchers, and photographers with meteorologists, and we connect everyone with the weather. Whether you are working in the world of weather and climate, or just have a curiosity about the world around you, we are here for you. Join us in empowering future generations. Join us to learn something new. Join us on your career journey. Join us in our passion. Join us.
Great, thanks, Kat.
So many
next slide now. Just a bit of
conversation
membership itself.
So
I always find it difficult to get off that video as well. I'll keep showing it. So yeah, just a bit of information on this slide about membership. I'm sure many of you are already members of the Royal Met Society, but if you aren't, then you can see the website link at the bottom of this slide and find out more about becoming a member and the benefits of being a member of the Society. And then I think my final slide is just some information about the accreditation schemes that we run at the Society. So we have the registered and chartered meteorologist. And again, if you want more information about these, then please do visit the membership websites where you can gain more detail about what they are and how to apply if that's of interest. Okay, so I'm going to introduce our first speaker, and delighted that we have Mike Kendon, who is a climate information scientist at the National Climate Information Centre at the Met Office. He's lead author of the Met Office's State of the UK Climate Report, which is published in the International Journal of Climatology. And so I'm delighted he's here to actually present the report itself and information from the State of the UK Climate Report 2023. Over to you, Mike.
Great. Okay. Thank you, Liz. Just share my screen. So hopefully you can see that okay. So I'm going to talk a little bit about State of the UK Climate 2023. As Liz says, I'm lead author on this report, but of course, a report like this is a very much a team effort, you know, with significant contributions from everybody in our team at the National Climate Information Centre named there. But before I talk about the report, I thought I would actually just like to start by looking at the rainfall that we've just had at the end of September, as our role in the National Climate Information Centre is monitoring the UK's weather and sort of climate context. So it's good to keep things up to date. So this map, the maps here show the last 10 days of September just gone, where we had some really quite significant flooding across central England. And you can see we've had about 150 millimeters or more in red in the wettest areas. And in fact, this is right in that the middle of that area, 3 times the monthly average rainfall in just the last 10 days of the month alone. And some fairly remarkable statistics for this event. We had Oxford's wettest calendar month for 250 years, and the highest 2-day total on record for Oxford in a near 200-year record, absolutely smashing the previous record. And in the bottom right, you can see a time series showing Oxfordshire rainfall for September based on our HAD UK grid data set from 1836 to 2024. So the question I'm just going to pose, I'm not really going to answer it, but I'm going to pose it is, should we be surprised to see events like this in the observations, and what conclusions can we draw? And the reason I thought I would just ask that question is to point out one thing that we have to be so mindful of when we're looking at extreme events is event selection bias. So in other words, I've decided to show that chart because I'm interested in September. I'm interested in Oxfordshire, and 2024 is the year I've happened to shown it. So there's this big extreme. So I've selected what I'm showing based on the data that we have. So that's an important point to consider when we're looking at these types of event. The other thing I wanted to just briefly touch on is where we're heading for the year overall. Our press office in particular is particularly keen to know what we're looking likely to have. So in the table on the top left, we've got values for what the UK annual mean temperature is currently and where we estimate it's going to be if we assume average temperatures for the rest of the year. If we had average temperatures for the rest of the year, we'd end up at about 9.54 degrees Celsius, ranked about 8th in our series back to 1836. So there's still another 2.5 months to go, but it seems like at the moment we're heading for another top 10 warmest year in 2024. And the chart on the top right is showing the UK annual time series for mean temperature from 1884, with 2024 shown as marked. And it's not as warm as, it's not going to be as warm as the last 2 years unless we have a really spectacular heat wave in the last couple of months of the year. Tempting fate there saying that. But, you know, it's worth pointing out that it would still be, if that happens, still be warmer than any year in the 20th century. And in common with a lot of years that we've seen recently, you know, there's a lot of variability in temperature through the year, but you can see in the bottom right chart, on the whole, we have more days of above average temperature in red than below average in blue. And the other thing to point out is it's going to be another wet year. Most of central England has actually already had the full annual average rainfall. So that's hot off the press as of perhaps about an hour ago. So what is state of the UK climate? So this report is published into the International Journal of Climatology every year. We look at the most recent year and the most recent decade, which provides a snapshot of where we think our climate is at, based on observations primarily from the land station network of the weather stations across the UK. And we're comparing those against 30-year averages for 1991, 2020 and 1961, 1990. And of course, our long-term climate series that we have based on gridded data, which I'll come to in a minute, going back to the 19th century, and also the very long-running Central England temperature series back to 1659. And I did want to talk just a little bit about the data set behind this report. We generate in the NCIC team the HAD UK grid data set, 1 kilometre gridded climate data for the UK. We write the software to generate this data set ourselves called Climate Grid. It's Python based, and we spend a lot of time in our team managing the code and the software systems to ensure that the climate products are traceable, reproducible. And the data set itself, we're regenerating in its entirety every year. And that is so that we can take advantage of more digitized data as and when it becomes available, so that we can push records back. You know, we can push our series further back into the past and really maximize the benefit of further digitized observations. So in the middle, we have a map that shows where the station network is currently across the UK. There's about 400 stations in the network. And what we do is we interpolate those onto a regular 1 kilometre grid using an inverse distance weighting approach, so that stations closer to the grid point have more of an influence than stations further away. And that enables us to produce products like the one on the right you see here, which is a map showing rainfall during Storm Babette in October 2023. And you can appreciate over time, the station network has changed a lot. Stations come, stations go. But essentially, because we're gridding the data, if we were to choose a different set of stations, we would still see, broadly speaking, the same overall result in the products that we get. And gridded data are not prone to the gaps that we see in station observations. So there's good reasons for gridding climate data. And the data are available on the Centre for Environmental Data Archiving, CEDAR website, under open government license for researchers or for government, for business, and for the community to look at. We also produce statistics. There's a lot of statistics in State of UK Climate based on areas. So effectively, once we have this gridded data, we can calculate area averages from the gridded data points for different sets of areas. So for example, the UK, countries of the UK, or climate districts. I think it's something like 8 or 9 climate districts we monitor. And it's a bit hard to see here, but I did pull out a map from Met Office Weekly Weather Report from December 1915, which basically shows the boundaries that we're still using today. So those boundaries for climate districts go back a very long way. And we also monitor statistics for county areas. We try to use a stable set of areas. We're using a set called ceremonial counties, because we don't want to continually have to update our statistics every time there's some administrative boundary. So effectively, we're treating them as fixed in time. And we can produce statistics for other areas too. So, for example, hydrological areas, the map on the chart on the right is showing river catchments for the Environment Agency. And that happens to be showing what the wettest year is on record in our series for different river catchments. So the wettest winter is. So in the southwest, for example, much of southwest England, really, it's 2014. In Cumbria, it's 2016. Of course, that was when we had Storm Desmond. And in East Anglia, it's 1915. So it's a good way of being able to summarize what we're seeing in our data quite quickly, quite straightforwardly. So if we look at 2023, we had the second warmest year on record for the UK and CET in series from 1884 and 1659. The 10 warmest years in the UK series have occurred this century, and the most recent decade is the warmest 10-year period in the UK and CET series. And we're running about 1.25 degrees warmer than 1961-1990. In fact, it was the warmest year in Ireland in a series they have from 1900. And you can see in the map on the right, 2023 was actually the warmest year on record for counties in the west of the UK. 2022 was the warmest year on record for most of the UK, but a few earlier years in the far north. And in common with a lot of years, we had several months in the year, a lot of recent years, several months in the year in the top 10 warmest, as happened in 2023, including the warmest June and equal warmest September on record for the UK. And you can see that in the time series chart on the bottom left as well. So what does this tell us in the context of where we're thinking we're going to go next? So the top right is showing our observational time series from 1884 to 2024, showing where we think it's going to end up. And those same observations are plotted in the bottom right against climate projections going out to the end of the century. And the grey plume is showing a representative concentration pathway 4.5. That's an intermediate pathway, emissions pathway going into the future. There's obviously a range of possibilities depending on which pathway we have to choose in the future. But basically, fluctuations in central England temperature have been, broadly speaking, within a half a degree in the last 300 years. We're now looking at 2 degrees of warming in the next 80 years. So our climate's going to go well outside the envelope of the current and historical range. And there's a potential for far higher annual average temperatures, not just annual temperatures, not just in the future, but in the current climate as well. So in fact, a year like 2023 will be a fairly average year by the middle of the century and a cool year by 2100. So that is obviously of profound concern. And climate change dominates occurrences of temperature records. So in these charts, we look at how many months, seasons, and years fall in the top 10 warmest and the top 10 coldest in each decade of the 140-year series that we have, aggregating across all county areas. And we've reached a point now where roughly 1 in 4 months, 1 in 3 seasons, and every other year is in the top 10 warmest. That's what we've seen based on the most recent decade. And virtually no months, no seasons, and no years in the top 10 coldest in the most recent decade. And the difference in those numbers between month, season, and year, it relates to the signal to noise ratio. So in other words, as we average over time, the natural variability in our climate tends to get averaged out, whereas the climate change signal remains. So we see a greater to signal to noise ratio and a greater proportion of records annually than, for example, monthly records. And climate change also increases the frequency of temperature extremes very clearly. There's an analysis in the report, which we've also included, which looks at the number of days per year where we've seen what we described as pleasant, warm, hot, very hot, and extremely hot temperatures. So this is 20, 25, 28, 30, and 32 degrees Celsius. And when we look at 1961, 1990, 1991, 2020, and the most recent decade, you can see the areas in red, the count of the number of days where we've seen temperatures exceeding those values dramatically spreads across the UK. In the bottom chart provides some summary statistics, which is probably rather a lot to take in the short space of time. But essentially, if we look at the most recent decade compared to 1961, 1990, and we look at the percentage increase, if we look at comfortable days, we've seen about a 40% increase for the most recent decade compared to 1961, 1990. Warm days, about a 60% increase, whereas hot days have more than doubled, and very hot and extremely hot days have more than trebled. So what that is telling us is that the greatest proportional increase occurs in the number of these days occurs at the higher thresholds. And clearly that's extremely important when we're thinking about things like public health. So the implications of our changing climate is that we will see that most notably in the extremes. And it was also a wet year, the 7th wettest year on record for the UK. 5 of the 10 wettest years have occurred in our series this century. And we're about 10% wetter than 1961, 1990. The chart on the right showing the wettest year on record, you can see there's a lot more variability across the UK than the map for temperature. But you can see we've got 2019, 2015, 2012, 2011 appearing in there. And I'm sure we'll continue to see more recent years carrying on, appearing in that map. And in terms of the year overall, March, a wet March offset a dry February, a wet July offset a dry June. But in the end of the year, the wet areas tended to coincide, so that really had implications for flooding towards the end of the year. I've got maybe 5 minutes, have I, Liz?
So probably just a couple more minutes, Mike.
Couple more minutes, okay. It's very hard to compress everything to such a tiny space of time. It's quite frustrating, but never mind. I'm going to skim over the previous slide, just mention Storm Babette. This particular storm, this was the most impactful weather of the year. We had stationary fronts. We had a low pressure coming up from the south, picking up a lot of moisture over the Bay of Biscay. Stationary fronts blocked by Scandinavian high, and extreme orographic enhancement in an unusual southeasterly flow with some very, very wet weather across eastern Scotland, Angus in particular, and widespread, prolonged, extensive flooding to all 4 nations of the country. I believe that Matthew is going to talk about Storm Ciarán, so I'm not going to steal his thunder and move straight on from that chart as well. And just to summarize, this report is about the observations and what they tell us. It's very clear our climate is continuing to change. Recent decades have been warmer, wetter, and sunnier than the 20th century. The observations show that it's the extremes of temperature that are most they're affected most by the fact our climate is changing. And what we're seeing for the UK is broadly consistent with what we're seeing globally over land. And we know from attribution studies that the warmest year, the second warmest year in 2023, the warmest June and September heat wave were all made more likely by climate change. But critically important, none of this would be possible without the observations. So the quality and continuity of observations are critical to our understanding of climate change in the UK. And I'd just like to kind of end on that thought and also just finish with some, images of, imagine being one of these people affected here, how devastating that must be. And I'm afraid we're going to see more of that in the future. So with that, I'll stop. Thank you very much.
Okay, thanks, Mike. Really good. As you say, it's a long result. There's a long report. Sorry, there's a lot of detail in there, and I would encourage people to go and look at the detail. But I think that was a really excellent summary. Time for a few questions. So if we have a couple of questions, please do put them in the Q&A. While I'm waiting for some questions to pop up, Mike, I just wondered, you did a really nice summary at the beginning about how how you collect the data and using the HAD UK grid data. Are you looking at using AI at all to kind of so you talked about within a grid square, you might have a few observations. Is there any way of kind of adding value to that by considering where the observation may be with regard to, orography, so whether there's an orographic effect on the data? Is there any AI that's being used or planned to be used in future?
It's a great question. I think we briefly discussed this at the recent conference that we had over the summer. I mean, there's obviously the Met Office is thinking very hard about where AI is going more widely in the work that we do. In terms of what we do specifically, there are a number of places where it might be applicable. One of the challenges that we have is with quality control of our observations that go into our gridded data. So there is actually a team based up in Edinburgh that managed the quality control of the observations in the MIDAS database. So this is the archive of historical observations from the land surface network for the UK. And they have a number of tools that they use to sweep data and look for suspects. And we have tools as well to try to remove suspects. And when we're doing that, we're always trying to balance two things. We're trying to get what we would describe as hits, correctly remove suspect data. We're trying to miss as little bad data as we can, but equally we're trying to avoid removing good data. So which is that balance between misses and false alarms. That's the key thing. And I think we have to be very conscious that we don't over smooth. So often with observations, one of the key things is the interest is in the extremes. And one of the worst things we can do is to over smooth the data. I think the other thing is clearly rainfall is probably the most impactful variable, arguably. That is perhaps one of the most challenging to address. So I think while AI might sound great, I think the reality is it's quite a big ask when you think about the challenges that we have. So I think we need to explore it further, but I think we need to be quite cautious and bear in mind the caveats that I've mentioned.
Yeah. Great, thanks, Mike. It's a question from Gareth, and I might get you to answer it in the Q&A actually when we move on to the next speaker, but it's about maybe using WOW data to do some sort of validation on or to add to that database. So I'll let you answer that in slower time. But I think you're right, Mike. The averages are really important, but the extremes are the things that have the biggest impact. And it's great to see this report now has more information about the number of extreme days or events, whether that's heat or rainfall, being shared. You had one slide on that. That was great. So thank you, Mike. One other thing that the report has had in recent years is phenology. So that leads on nicely to our next speaker, Judith Garforth, who is a Woodland Trust Citizen Science Officer and puts together information for Nature's Calendar report. So she's worked on citizen science as part of the citizen science team at the Woodland Trust now for almost 9 years. And Judith, phenology is a key part of this report. So I'm really keen to hear your presentation on Nature's Calendar. Over to you.
Yeah, thank you very much. Yeah, so as Liz just said, I'm Judith and I look after the Nature's Calendar project, which is one of 3 citizen science projects run by the Woodland Trust. The other 2 are the Ancient Tree Inventory, which is about finding and mapping ancient trees, and Observatory, which is about tracking tree pests and diseases. But Nature's Calendar is about tracking the changing seasons, and it's a phenology project. So phenology is not a very widely used word, so I'll explain it here. But it's the study of the timing of recurring biological events, and often in relation to climate and weather. And these events that we talk about, they're parts of the annual life cycles of plants and animals. So it's things like the leafing of trees, the flowering of plants, emergence of insects, migration of birds, evidence of breeding, all those types of things that form life cycles. It's tracking how they change over time and how that relates to the weather and the climate. And phenology is important because as Mike was just explaining, some of the impacts on humans of extreme weather like flooding, and we know what the impacts are to ourselves as a species, but what's the impact on nature as a whole? And phenology can give us a bit of an indicator of what's happening to wildlife as a result of weather and climate. Unlike weather, though, phenology is a little bit more difficult to measure with instruments. We can't record phenology on a thermometer or a rain gauge. Slightly, you can use fixed point photography, or satellite imagery, but on the whole, it relies on people power. And that's why it works so well as a citizen science project. So the Woodland Trust has a network of hundreds of volunteers, and they're based all over the UK, and they are our eyes on the ground. We couldn't do this without them. And they're all monitoring the timing of the seasons changing where they live. And by sharing that data with us, we get a much bigger picture of what's happening all over the UK. So there are 69 species in the project and over 150 seasonal events in total. And it's dates that are really important. So our volunteers are telling us dates of when these certain events happen. And despite it being run by the Woodland Trust, it's not all about trees by any means. There are lots of trees in the project, but there's also amphibians, flowers, grasses, fungi, insects, birds and shrubs. And partly the reason for that is that it maps back to more historic projects, which I'll come on to in a minute. But also it allows scientists to have a look at the effect of small changes in timing and how that affects food chains, and how a small change at one end of the food chain can have a bigger impact as you go up the food chain. So there's a big variety, and there are seasonal events to record all year round. So it starts in spring in January with things like hazel flowering, snowdrops flowering, and continues all year round, leafing of trees in the spring, flowering of plants, and then autumnal changes as well. Leaves changing colour, trees dropping their leaves in the autumn. And you can get a calendar of events that's shown on this slide on our website. You can download that. So you get an idea of when different seasonal events are likely to occur. So once our volunteers have spotted a seasonal change where they are, they submit that date to the Nature's Calendar website, and that goes straight into our database and can be used by scientists for research. It also goes onto our live maps. Here's just one example for you. This is a map showing bramble ripe fruit in 2020-24. So the earliest bramble ripe fruit we had this year was the 3rd of July. So that's our blackberries. We get our volunteers to monitor a shrub near them regularly. That's like at least once a week. So they notice when things happen for the first time. I think we all know when a blackberry's ripe, it's when it's nice to eat, but for all our other fruit, we say it's when they're soft to touch. They tell us that date. So the first was on the 3rd of July. If we fast forward a few more days, then 20th of July, you could start to see the green dots spreading further up the UK. Fast forward a bit further into the autumn, and towards the end of the autumn, you can see we've got records all over the UK there. Okay. So as well as collecting data now and into the future, the Nature's Calendar project has involved digitising historic records and adding those to the database. So Nature's Calendar was originally founded by Tim Sparks in 1998. And at the time he worked for the Centre for Ecology and Hydrology. And he ran 2 pilot years of the project and it was very successful. At which point in 2000, he asked the Woodland Trust to get on board to help bring it to a much wider audience so we could get more volunteers involved collecting the data. And it's been run by the Woodland Trust ever since 2000. So we're coming to our 25th anniversary this coming spring. But as I say, we've also got data going back as far as 1736. So our oldest records come from Robert Marsham, who owned an estate in Norfolk and recorded for his lifetime. And then successive generations of his family continued that recording on the estate for a very long time. But I thought I would highlight here the orange bit on this timeline. This was a national recording scheme run by RMETS, by the Royal Meteorological Society. At the peak of that project, there were 600 recorders. It's a bit like Nature's Calendar. They were volunteers and they recorded a variety of different seasonal events. And when Tim set up Nature's Calendar, he made sure that the same species were being recorded so that we could continue that record further into the future. Unfortunately, in 1947, RMETS decided to stop the project and they couldn't find another organisation to take it on. So that's probably just a good point to stop and say thank you to our current funders, which is the People Postcode Lottery, because without funding, these projects are hard to continue. And if we don't record this data now, we can't go back and get it. So it's so important to keep them going. So thank you to PPL. As you know, the difference between weather and climate, we can look at the weather in an individual year and see how that affected nature that year. But to really understand how climate is affecting nature, we need that longer term time period to make the conclusions, draw conclusions. So one piece of work we do is called the Spring Index. And this is basically just one little way of answering the question, is spring getting earlier? And so what we do is we take the data from hawthorn first flowering, horse chestnut first flowering, the date that orange-tipped butterflies are first spotted in spring, and the date that swallows are first spotted in the UK after migration in spring. We combine all those dates together for the whole of the UK to create a single index and look at how that changes over time. And so here we go, here's the graph of the spring index. The first thing to notice is that it's really zigzaggy. So the index changes a huge amount from year to year. There's loads of variability. And that's because some springs will be warm and everything will be earlier, and some springs will be later and everything, but some springs will be colder and everything will be later. And you see that over the whole time frame of the graph. It's really variable. But what we do spot on this graph is that the green section at the left of the graph, that's data from the Royal Meteorological Society recording scheme. And if we compare that average to the average from the Nature's calendar 25 years, you see there's a difference in 8.7 days. So it's a suggestion that spring is now over a week earlier than it used to be. This is only one little bit of evidence. If you pull that together with evidence from other sources and other projects, they're finding a similar thing. But I just wanted to show you this because it combines data from the two recording schemes of interest. So I've been asked to talk a little bit about 2023. So we're delighted that Nature's Calendar now contribute a phenology section to the State of the UK Climate Report. And it just gives a bit of an indicator of nature's response to weather in that year. So because the Nature's Calendar project has almost been running for 25 years, our baseline in the report is a little bit different. We have to compare the current year, so 2023, to basically the rest of our data, 1999 to 2022. We'd love to have a 30-year average so we can work on the same terms as weather data, and we're getting there, not too many years to go. But at the moment, that's how we have to present our data. And the report is a summary of the whole project. So we've got that 150 different events you can record. But into this report, we put 4 trees, 4 flowers, 4 invertebrates, and 4 vertebrates. And actually for phenology in 2023, most of those indicators were very near their baseline. There were just a few exceptions. And we noticed that the leaf-on season, so that's the difference between when the trees first get their leaves in the spring and when they drop them in the autumn, which is a bit of a proxy for growing season, that was 4 days longer than our baseline. And this year, that was largely due to a later autumn rather than an earlier spring. Some years we've seen it stretch at the other end, but 2023, it was stretched at the autumn end. But probably one of the most interesting things we noticed in the data in 2023 was that hazel had its earliest flowering date in the whole of our series. So I don't know how familiar you are with tree flowers. They're not always the most obvious. Hazel trees have male flowers, as I've shown in the photo. They're catkins and they flower very early in the year. You can see them in December sometimes, January, February. They start quite small and then they expand and then they release yellow pollen. And these are the male flowers. And then the female flowers, they're tiny, but they're like sea anemones. They're bright pink and they're shaped like sea anemone. They're like fuchsia. Once you spot one, you can't not see them. They're so unusual. But it's the opening of these male catkins that our volunteers look out for and record the date of. And we know it's influenced by the temperature between December and February. So we've worked out that for every 1 degree centigrade increase in temperature in those months, the flowering will be 5 days earlier. And we know from the temperature data in the report that February temperatures were well above average in 2023, which probably explains the early flowering. But perhaps even more interesting than the fact that we had an extreme year for hazel is that now over the 25 years of the Nature's Calendar project, we're starting to see a very slight trend in hazel flowering. So on this graph, we've got flowering for 4 species. There's wood anemone, which is the blue, lesser celandine, which is the red line, and bluebell, which is the green line. And those other 3 flowers, which flower later in the spring, it's fairly constant. I mean, there's variability from year to year, but there's no obvious trend. So it's quite interesting that hazel flowering is starting to show a significant trend of flowering earlier. And I've pulled this graph out of the report as well, because I thought it was quite interesting that it split the temperature by season. And I've just highlighted in a circle and expanded that last bit of the graph, because that's from 2000 onwards. So that's the bit that Nature's Calendar has been recording. And the yellowy orange line at the bottom is spring. And that seems to have increased in temperature a lot less than the winter, which is blue. And it's those winter temperatures that's affecting hazel flowering, but it'll be those spring temperatures that are affecting the wood anemone and the bluebell and the celandine. So that probably explains, at least partly, why we're seeing a trend in some flowering and not others. But really, to me, the interesting bit is the so what. Why does it matter if hazel flowers earlier one year or is getting earlier every year? But it's a trend we'll definitely be keeping an eye on over the coming years. It might be that we get a late year and in a couple of years' time, and that trend might turn out not to be such a trend after all. It might even out. I can tell you, sneaky preview, that provisional data from spring 2024 does look like another early year. It won't be the earliest, I don't think, but it is looking like that trend isn't continuing for another year. So what implications will that have? Well, hazel flowers, because they're wind pollinated, release a lot of pollen into the air, and it is a human allergen. So that has implications for the hay fever season for people that are allergic to tree pollen. It might have implications for hazelnut production. So the catkins, our volunteers, monitor other male flowers. So it raises questions like, will the female flowers open at the same time as the male flowers? Will pollination be as successful? Will that mean that the hazelnuts that develop from the female flowers ripen earlier? Will there be as many? Will the yield be as high? There's lots of questions really it raises. And then what does that mean for the wildlife that feed on them? Dormice, for example. So the phenology side of the data tells us more about the impact on nature and raises lots more questions. So that brings me to the end really, other than to say, if you are inspired to take part in the project, we would absolutely love to have you on board. There are still things to record left this year. So depending where you are in the country, it's probably full autumn tinting is probably the next seasonal event. Sitting here in Yorkshire, our trees have started to tint, but hardly any I've seen are at full tint. So that might be something you can spot when all the leaves on a tree have changed colour. And then also when all the leaves have dropped and your tree is completely bare. So there's 2 dates to keep on looking out for. So if you are interested, head over to the Nature's Calendar website. You can register anytime. You can start recording anytime. And also just to say a big thank you to all our volunteers, because without them, none of this would be possible. So yeah, thank you very much. And if you've got any questions, I'd love to answer them.
Brilliant. Thanks, Judith. Really interesting. As I say, phenology is a really fascinating part of the State of the UK Climate Report. I think really important because it shows the impacts of how the weather has both on that year, but also that kind of change, the climate change impact as well. So really good. Thank you for that. So we have a question from Gerald. So do we know how much influence rainfall and sunshine amounts have on phenology? I guess it depends which aspect you're looking at, but maybe you could choose a couple where rainfall and sunshine amounts have, you know, a significant impact.
Yeah, I can certainly say that spring is a little bit more straightforward. So our spring events tend to be, you can regress them against their timing against temperature, and those regressions are quite strong. And you can see that they're really strongly affected by temperature. Autumn phenology is so much more complicated because For example, the changing of leaf colour in autumn and the dropping of leaves depends on whether we've had a drought during the summer. It depends on storm events, depends on rainfall and waterlogged soil. So there are so many more factors that play into autumn phenology, which makes it much harder to analyse. But also, Nature's Calendar really is the first project to record the autumn data. A lot of that historical data I showed on the timeline is all spring data. It comes from people's own personal nature diaries, and they were just must have been more inspired by spring. They must have got through that gloomy winter and thought, thank goodness I've seen my first snowdrop. I'm going to make a note of that. But the same didn't seem to happen in autumn. There was less of, oh, winter's coming, let's write about that. So there's like this dearth of autumn data compared to spring. So that, and the fact that it's more complicated in terms of rainfall events and storm events, makes it more complicated, but more interesting to analyse.
Great. Judith, are there any parts of the country where you find either there's a big uptake in people who get involved with Nature's Calendar, and probably more importantly, where there are gaps, parts of the country where you'd like more people to go out and do some observations and record it?
Yeah, so we've looked at our recorder spread over the UK, and it does have a southern bias, and it always has done for the whole of the 25 years. It basically vaguely maps with population density. So we have to bear that in mind when we analyse the data, but that skew it's been a consistent skew over the 25 years. But we do need volunteers all over, and we need a good number of records for every single species and event to be able to even consider doing a UK average. But really we want more than that, so we can say, oh, how is Northern Ireland different to Northern Scotland, Southern Scotland, Northern England? And it is very different. We know just from those live maps, if you play with the sliders, you can see spring in particular starts on the very southwest tip of Cornwall, and you can see the dots creep further up northeast as spring progresses. So we know there are these differing trends over depending where you are.
Brilliant. Okay, thanks, Judith. A really fascinating part of the impacts, I guess, weather and climate have on the world around us. So I'm going to move on to our third speaker. Delighted that we have Joanne Williams, who is a sea level scientist at the National Oceanographic Centre in Liverpool, specialises in time series analysis of tide gauges and storm surge modelling. And another important aspect of the State of the UK Climate Report is the oceans around our shores, and particularly sea level as well. So I'm going to hand over to Joanna to give us an update. Over to you.
Thank you, Liz. So I work at the National Oceanography Centre, and I look at the tide gauge records and the models of storm surge around the UK. So whenever we have a high water event, it's a combination of the tide, the storm surges that change the water over just a few days, and then over the long-term climate sea level rise parts as well. And the UK tides are huge, so that's always a really big effect here. So we take data primarily from about 40 gauges around the UK. These are our key gauges, and these are used for the daily forecasts of surge as well. And yes, so the tide is huge, and the biggest effect we have everywhere is the difference between spring tides and neap tides. We've got here the full moons and new moons, and that's always the biggest effect at most sites, especially in places like the Severn Estuary where the tides are very large. We've got up to 14 meters in Avonmouth. So that's a huge effect there. But then when we looking at surge events, what we do is we take off the predicted part of the tide that's due to the lunar cycle, and then just look at the difference between that total water levels and what we would expect from the astronomical predictions. And that tells us something about storm events and particular events that happen. And so obviously there's a huge amount of information there, but we look at particular events through the year. Some of these are named storms that I know that later on somebody's going to be talking about Storm Ciarán. That's very significant in Jersey. But other named storms through the year, Pier and Garrett towards the end of the year were very big ones for surge. Sometimes, though, the big events are other storms that are not named, they're not being picked out particularly as being very high wind events, but just because of the configuration of the storm, it can still be significant in terms of surge. So we're often on the lookout for those too. And so, for example, here, the biggest tides of the year, this event in March, was particularly high tides. It happened to fall on the spring tide as well. And so a relatively small storm, it wasn't a named storm, but it happened to fall on the spring tide. And so that was the event that had the highest surge levels, the highest total water levels at most of the west coast of the UK, and down to the Severn and up through Scotland. When we look at the autumn part of the year, again, lots of named storms there, but actually most cases the named storms weren't the most significant events for total water level. Again, it's the event in October where the very high tide happened, and that was again very high totals in much of the UK. Ciarán, unfortunately, we didn't have any data from Jersey, so we don't actually have that information because the gauge was damaged. And so typically you get the storms tend to affect one side of the country or the other. Pier was an example where that was very significant in the North Sea area. Very high skew surges, so the difference between the predicted astronomical part of the tide and the total water level in lots of the North Sea and across through to the Netherlands and Denmark as well. But fortunately, it fell on neap tide. It didn't fall near full moon or new moon, and so the total water levels were not so severe as they could have been. I mean, if it had been a week later, it would have been more significant. And yes, again, this one here in March, it was the high water levels in general more than the severity of the surge. Only 3 Thames barrier closures last year, and again, they weren't all associated with surge events. But when we look over the year, we get, we've got lots of data that's just about good enough for looking at single storm events. But for climate events, climate quality data, we need to have much higher quality information. We want to make sure there's absolutely no false positives in there, no drifts in the information. So it's much thinner what information we have. And unfortunately, we weren't able to get together the UK sea level index this year. But we do have good data from Newlyn, so we kept able to carry on the long-term information from there. And so we can continue that data on the average sea level over the whole year. So this was in the report with Mike this year, and it's an unusual way of presenting that, but I think it's been quite valuable to look at, is to think about what part of the data are we fitting the trend over. So we've got good data going back right through the 20th century. So if you fit sea level trends over that full period of that, then it's about 2 centimeters a decade sea level rise. But when we look at the earlier part of that record, that was that sort of size rise. But towards the end of the record, we've got much greater rises in sea level going on, and the shortest period it's reasonable to fit a trend over sea levels here in this area is probably about 30 years because of the interannual changes that you get. And when we look at that, you can see that we've got this much more significant rise going on in the last 30 years. And so that's now up to about, or was 15 years ago, up to about 4.5 centimeters a decade. So that's the sort of sea level rise we're getting at Newlyn. So when we look from one year to another, hopefully this will work. Let's see if this goes. So we can plot sea level through the year. There is in most sites a bit of a cycle in the sea level through the year as well, where sometimes a year is slightly higher. Tend to get a higher sea level towards the autumn. And when we plot successive years gradually building up, we can see that that rise in there. So it's getting to the point where the rise is greater than that annual cycle there. Just let that carry on running for a second, and we can see those years gradually increasing there through Newlyn. Up to the most recent, well, that's 2023. We do now have data up to 2024, hot off the press up to August. And again, that's carried on. And yes, that year there, 2023, the autumn of 2023, that's about 10 centimeters higher than has ever been recorded before at Newlyn. It was quite a substantial rise there. And it wasn't just seen at Newlyn. Can see that this is something that's been seen pretty much everywhere around the country as we go through in time. You get this annual cycle in lots of places, and then the more recent data is almost always is at the top. That's sea level rise that we're seeing there. Newlyn is not unusual around the world. These sites around the UK this is pretty typical of what we're seeing everywhere. So these are from satellite data here. We've got the red color is rises of around 10 centimeters or so over the last 30 years. The average sea level rises around 10 centimeters. Just a slightly closer look at Newlyn. It's slightly more than the global average, but not massively so. And that's due to two basic aspects. One is that there's an increase in the temperature of the water, which makes it expand slightly, not as much as air expands with temperature increase, but it does expand a bit. And that has a direct effect on the sea level there. And then more water in the ocean as ice sheets melt, global ocean mass changes, and then that literally adds more water to the oceans too. And if you add those two effects up, you get this total sea level rise, and they do add up quite nicely now. that budget has been closed, and that's what we're seeing. So that's the global picture in total there. Those global numbers don't seem to matter hugely. And 10 centimeters, it seems quite a small number when you compare it to the tide going in and out by 10 meters every day. But again, it's to do with how often you reach those extremes. And when you increase the mean sea level, add a little bit onto the mean, what you do is you push that tide up the beach or up your harbour wall that a little bit further every day. And those extreme levels that you would previously have only seen very rarely, we will be seeing more frequently. So, whistle stop tour. I think we're on time. So I shall stop that.
Great, brilliant. Thanks, Joanne. As I say, I think a really fascinating addition to the State of the UK Climate. It's been in there now for a few years, and I think it's really important that there is a focus on the coasts and oceans around our shores. So thank you very much for that. There are a couple of questions in the Q&A. The first one, you did mention, obviously, the gauge was out during Storm Ciarán in Jersey. Was the gauge damaged by the storm, or was it just
no, that was just unlucky. It was already out a few days before, unfortunately. So yeah, so we just don't have have any data from that. Obviously there's lots of other records of what happened there, but not the standardized tide gauge data.
Yeah, a bit unlucky then, but I guess that happens from time to time. I guess there's work done on the gauges, and just unfortunate the timing of these things, but yeah. And then a question from Len. So I'm never sure when prediction of sea level rise in global warming scenario is given whether storm surges are included. Evidently not, as only few centimeters per 5 years are given. So is it getting windier and therefore storm surges may be more common? Analyses of North Atlantic storm frequency and track required. So yeah, maybe just a word around storm surges in this data, but also I guess the impact of sea level rise on storm surges frequencies, and impact.
We do tend to separate it. So when we talk about global sea level rise, we're usually talking about averages over quite long periods. So the effect of the storm gets averaged in with those periods where it's not stormy. But how much it will matter kind of depends on where you're looking. So in some parts of the world, the change in storminess is really significant for those extremes. But nearly everywhere, the change in storminess is not as big an effect as the change in the mean sea level. So when you look forward to 2100 and beyond, especially in the higher scenarios, you're adding on over a meter of sea level rise, then that's a bigger effect than the change in storminess would bring in terms of how often extremes happen.
Yeah. So the rise in sea level, I guess, means that when we get these storm surges, they are bigger and higher because of the sea level rise as the main contributor. Great. And one question for me. So you had a really nice breakdown of the different changes in sea level around the coasts of the UK. Do you notice that difference of the glacial rebound? So Scotland rising and the south of England kind of sinking. Is that factored into those numbers, or is that removed as a change in
that's in those numbers? So that's just the data at each site. So potentially like one site you could have some potentially some massive subsidence, and that would all be in there as well. Because that is just about those local points. But then when the tide gauges are used to calculate global mean sea level, then you have to take out those localized effects and correct for those first, and then you do the mean sea level, and then you would go back from those mean sea levels to whatever is happening locally. So in that particular plot, it would have been anything like glacial rebound would have been in there.
And you mentioned in 2023 the Thames barrier only shut 3 times. Is that quite a low figure? I don't really know how many times it shut. So
It's than it was last year. The previous year, rather, 22 was more. But yeah, I mean, I think originally when they built it, they weren't expecting it to shut it more than once a year anyway.
Yeah,
so,
indeed.
Yeah.
And finally, a question from Mark. So you showed the graph for sea level in 2023, and there was this quite significant peak in autumn. So do we know why the autumn 2023 sea level jumped? You know, why was it significantly higher, I guess, than previous years?
It's not absolutely certain, the attribution, but the Atlantic was very warm, and I think that's the most likely cause, is that really warm Atlantic.
Great, yeah. Brilliant. Thanks, Joanne. So we've had 3 talks. We're going to take a short break now until 3:15 UK time, if you're joining from not the UK. So back at 3:15 for our final speakers. We'll see you then. Okay, welcome back, everybody. I hope you had a chance to stretch the legs and grab a cup of tea. So we're going to move on to final two speakers for today's meeting. Delighted that we're joined by Matt Winter, who is a weather forecaster, many years of experience, but currently based at Jersey Met, and is the senior meteorologist there, forecasting across the islands in Jersey and Guernsey and beyond. And yeah, so this particular presentation is looking at one of those events during 2023, Storm Ciarán, which I know has been mentioned a couple of times. So with a focus of the impacts across the Channel Islands. So across to you, Matt. You're on mute at the moment, so I can't hear you.
In 2 seconds. Can you hear me now?
I can hear you fine now.
Perfect. Yeah. Sorry, technical issues here. Yeah, whenever I share my whole screen, the mute option comes on. So I'll just not share the audio on the presentation and hopefully that should solve it.
Okay.
So bear with me. Let's just try this one more time. This worked perfectly in practice, obviously, yes, but doesn't work now. Okay, hopefully you can see the presentation.
Yeah, perfect.
And you can hear me. Brilliant. Well. Cool. Thanks for the introduction. And I'm going to talk around Storm Ciarán and the impacts in Jersey and the Channel Islands. I'm also been asked to have a quick comparison with the Great Storm of 1987, given that it's the anniversary pretty much today. And as a little plot spoiler, there's the side-by-side comparison for the two. And I won't tell you which is which, but you can see the difference between the two right there. So I wanted to start off with just a summary slide, Storm Ciarán by numbers, running through some of the highlights of the storm, or the lowlights, depending on which way you look at it. It was one of the strongest storms to affect the Channel Islands in 36 years. We saw gusts in excess of 100 miles per hour. We also saw the lowest recorded pressure in November, 960.8 hectopascals. And we also saw a T6 rated tornado, which was the strongest to hit anywhere in the British Isles in the last 70 years, but also interestingly, the strongest in the records within northwestern France for over their 200-year record period. So a very significant tornado to affect the islands. Overall, 25,000 trees were felled or brought down or were needed to be felled after the storm. So for a small island, that's an exceptionally significant event. And during the peak of the storm, 169 people had to be relocated from their houses, mostly as a result of storm damage due to the tornado. And just trying to dig in the insurance report, I haven't got a quote in terms of the monetary value, but they saw a 600% increase in insurance claims over a sort of 2 to 3 day period. So that's normally the sort of volume they'd process in 6 to 7 weeks during the autumn period, and they saw that in 2 to 3 days. And in terms of financial cost, just the clear-up operation alone in terms of getting rid of the trees, etc., cost the government 2.75 million. But obviously that doesn't include any prices or any costs associated with rebuilds, repairing the hundreds of houses that were damaged, especially by the tornado. So just having a look at a sequence of events here, the storm started off not as a storm, as a fairly innocuous area of low pressure in the mid-Atlantic at 991 millibars, and then dropped over a 24-hour period around 35 millibars or hectopascals, so classifying it as an explosive cyclogenesis event. And that was as it tracked east-northeast towards the UK. And you can see with the storm track, the centre of the storm actually passed along the south coast of the UK. And importantly for the Channel Islands, what that meant was the strongest area of winds associated with Storm Ciarán. With these features, they're normally enclosed within the south and southwest flank of the storms. That was brought right across the islands and northwest France, which explains why Jersey saw so many impacts in association with this storm. The isobars were also very straight, so curvature of the storm wasn't really reducing the gradient wind speeds by much. So some exceptionally strong winds across the Channel Islands. couple of satellite images to go with that. So this is a midnight on the 2nd, or the early hours of the 2nd. The low indicated by the green cross and the L there, just out to the west of the area. But ahead of that, we saw severe gale force winds coming from a south to southeasterly direction. And along the surface, cold front conditions were conducive to develop some very severe thunderstorms, shown by the crosses there with the lightning strikes. So some very strong winds and severe convection ahead of the actual storm itself. And that actually brought us our strongest winds with the tornado that was spawned. And here you can see the low passing to the north, bringing that swathe of exceptionally strong, violent storm force winds across the islands, located around the south and southwest flank of the low. Also interesting to note is the area down to the southwest in the Bay of Biscay, where cold air has been brought over warm seas, developing another area of thunderstorms. So how predictable was the storm? Well, if you lived in south or southeastern parts of the UK, there was quite a lot of uncertainty around the track of the low, shown by this graphic here, with a variety of models 24 hours before the storm moved through. All of them was projecting or forecasting a similar track from sort of the west-southwest up to the northeast. But there was some variability on exactly where that track was, with the UK Met Office closest to the actual track of the storm there, highlighted in the black dotted line. But looking at the wider context of that, for Jersey and the Channel Islands, doesn't matter which of these models you looked at, the worst area, the strongest winds of the storm contained within that south and southwest flank were always going to be brought across the Channel Islands. So for Jersey and the Channel Islands, the storm was quite predictable in terms of the overall wind strength, and models were very consistent with overall wind speeds with this storm. But if you lived in the southeast of the UK, it was quite variable as to whether that low passed over the top of you or you had strong winds along the south and southwest flank. So just looking at an overview of some of the impacts from the storm, obviously I've mentioned we had a tornado which crossed the eastern part of the island, and that caused localized severe or catastrophic damage. I'll talk about that in a bit more detail in the coming slides. But we also had some reports of heavy precipitation, including very large hail within the dashed blue area here. And then quite a few of our automatic weather stations gave some pretty high rainfall totals through the event. So the highest there, Howard Davis Farm in the north of the island near Trinity, gave 54 mils in a 24-hour period, but actually 24 of that fell within 23 minutes. And we had 3 mils in a minute, which for Jersey is exceptionally high rainfall, giving rates of about 175 millimeters an hour. Obviously, the wind is the other main story with the storm. We saw gusts in excess of 90 miles an hour at pretty much all the reporting sites. Jersey Airport, our own equipment there, reported gusts of 81 knots, 93 miles per hour. And down at St Helier Harbour, we reported or recorded 83 knots, which is 95, and also some pretty high gusts at St Catherine's over in the east. Ports of Jersey have also got some airport equipment, which gave gusts of 88 knots at Jersey Airport. And we've also got a private system installed, a LiDAR at Lemoy Radar, and that recorded a maximum wind of 93 knots, but that was at 150 feet. So above the ground level and in a very exposed part in the southwest of the island. So I just want to flick through some photos of some of the damage, and just to draw your eye in as to where these locations are. So we've got the tornado path on the right, and I'll talk about that in a minute. But we've also got the railway walk, which is highlighted in the red dashed line. Now that's part of the old railway, which used to link St Helier to Corbière in the far southwest of the island. It's now been made into a walk or a cycle track, very heavily wooded, lots of trees along there. And a couple of other locations, Noirmont Woods down in the southwest of the island, and also Millbrook Park down in the south. So this is what the railway walk looked like pretty much along its entire length. So I mentioned 25,000 trees were brought down across the island. At least 600 of those were brought down across the railway walk, which just remained impassable for weeks, with the clear-up operation continuing kind of well into the winter period. So pretty much every section had trees down like this along the length of it. So widespread damage along a popular route that links southwestern parts of the island with town. Having a look at Noirmont Woods, I've got some satellite data here, which gives some good before and after images. So this is before the storm at Noirmont Woods, and this is afterwards, before and afterwards. So you can see how many trees have had to be cleared there. This is obviously well into 2024, once the tree removal equipment's been on site and removed and thinned out those trees. But just to give you an idea of how that looks now, this used to be a closed canopy pine woodland, and essentially it's been completely stripped in large parts. And even some of the trees that have remained standing have had, limbs torn off, aren't particularly in a great state. So aesthetically, quite large parts of the island have changed significantly as a result of this storm. So a bit further south, still around the Noirmont Wood area, you can see again large-scale tree fell within this wooded area. And what's interesting to note is this boxed area on the right-hand side. Actually, the ground drops away quite steeply towards the beach there. So you can see how much of a difference lee shelter makes, with the west side of this picture far more exposed than the east. Also deciduous woodland in there as opposed to pine. And I think pine trees have shallower rooting systems. So again, that might be some of the reasons for more damage there. And Coronation Park down on the south coast near Victoria Avenue, very popular spot for children to go and play and enjoy, especially during the summer months. Again, before shot and the after shot here, you can see how much the tree cover has changed within that area. Again, massively changed the kind of the aesthetic of how that area looks now. So moving on to the report, I think Sarah Horton's actually online. She's produced a very thorough report. She actually flew onto the island on the Saturday after the storm, and I met up with her and we went out to gather evidence for the tornado assessment. So both images here showing the track of the storm, but the left-hand one highlighting the rating, rated as a T6 in black, where we have evidence for that, and a T5 in red. And the right-hand side image just shows you the types of evidence that were collected, whether it was damage to trees, houses, buildings, etc. So what is a T5? What is a T6? Well, a T5 tornado has peak wind speeds estimated at somewhere between 140 and 160 miles per hour. And I think Sarah will probably agree that all these evidence descriptions were found on the island in association with the track of the tornado and pretty consistently along most of its length. But it did peak at T6, so it was categorized as a T6 with winds up to estimated 185 miles per hour there. And the things highlighted in the boxes were the evidence that we're seeing on the island. And I think one of the key pieces of information for categorizing a T6 is where debris gets lofted and thrown around so violently in a storm that it bends itself in structures. So lots of instances of roof slates, twigs, branches being thrown around the storm and embedded within doors, walls, etc. So very, very violent storm and very significant in the British Isles. So just having a look at the radar sequence for this storm, this is late Wednesday night towards midnight, the early hours of Thursday. We did have thunderstorm warnings out in place for this storm, and you can see some very intense echoes moving up from the southwest, moving across the island with some very heavy downpours in there. As I say, rates of 175 millimeters an hour in the core of that storm as it passed across the area. So very intense rainfall and some very organized structure to the radar imagery as well. Now, Matt Clark has done a really, really good paper using all the data from Jersey radar, and that's coming out, I think, in the next edition of Weather, so well worth a look through. But the left-hand image here shows the conceptual image of what a tornado looks like, along with the sort of mesoscale and where the large hail is found and the forward flank of the core. So that's on the left-hand side. And if you have a look on the right-hand side, this is the actual radar reflectivity image from the storm in question. So it just maps really well to what a typical storm looks like, including the hook there, the areas where heavy hail, large hail was reported, etc. So a classical tornado. And I think Matt has said that it's one of the very few times, possibly the only time, where a tornado of this strength has passed through a high resolution radar. So it's just providing an absolute wealth of data to study these features. So what did the hail look like? Here's some classic pictures. Very, very large hail, especially for cold season, given this was in November. Pieces measuring 5 to 7 centimeters across. And you can see on the right-hand image that actually some of those pieces of hail are sort of aggregated smaller pieces and have some very unusual shapes. And again, that's quite indicative of very violent motions within severe tornadoes, convective systems. So yeah, some very large hail. Fortunately, there wasn't too much damage from the hail itself. It was more the winds associated with the tornado. So hopefully this video will play. I don't know whether the sound will come through for you, but this is the only video in existence, I think, of the tornado. So I'll just let this play out. Obviously, it's in the dark because it was happening just towards midnight, but you can see the core of the tornado on the left-hand side of the image. Starting to lift debris now as it's interacting with buildings, roofs, structures. And then quite rightly so, the person taking the image, Ashley Matthews, then took cover. But yeah, a very violent tornado. And I think partly we were lucky that it happened around midnight when there weren't more people out, but also everyone was under a sort of government guidance stay-at-home order anyway because of Storm Ciarán. So some images of the damage that was caused in a narrow stretch, but across the whole length of the tornado's path. Damage to buildings, roof structures, outbuildings, extensions. But what I'd like to draw your attention to is this large beam on the right-hand picture leaning up against the wall. So that measured roughly about 5 meters, had a decent cross-sectional area. So we reckon it could have well been about 100 kilos in weight. And the arrow that has the 150 meters on it points to where that beam ended up, in that house's garden. And it actually came from that white building in the south of the picture. And so on the right-hand side, I've got a before and after of the roof structure that was ripped off. So the gable end was ripped off the table tennis building. And these beams were tossed 150 to 120 meters across that green playing field. And some of them didn't even touch the ground. So that just kind of embeds the idea of the power of these features when they happen. And this is actually my friend's house. They were fortunately away on holiday when this happened. So circled in red is the house across the road, which the arrow is kind of pointing to. And then the zoomed out picture sort of on the right-hand side shows you the twin boys' bedroom upstairs. Now, lots of debris was ripped off that house across the road, roof tiles, ridge tiles, slates, stones, bits and pieces of wood, etc., and thrown violently across the road, smashing through the window and then littering that bedroom. So massively fortunate that they were away on holiday at this point. And on the bottom left-hand image, you can see one of the ridge tiles has been thrown and embedded within some outdoor furniture. So again, very, very violent storm. And this is again just kind of showing you where that happened. So the buildings to the south, between 45 and 60 meters away, all that debris was kind of thrown northwards towards their house. So Storm Ciarán, comparison with 1987, were they similar systems? Yes, in lots of ways they were. They had a very similar depth. They happened at relatively similar times of the year, and they both went through explosive cyclogenesis and developed very quickly. And actually, I think in Burton Mansfield's reanalysis of the storm of 1987, they gave it a central pressure of 953. So actually exactly the same central pressure to these two storms. The main difference was that the way the storm moved in and its track as it turned to the northeast. So Storm Ciarán came through from a west-southwesterly direction and then turned to the northeast. And that brought the strongest wind across the Channel Islands in that south-southwest flank of the low. But with the Great Storm of 1987, it came from more of a southwesterly direction or a south-southwesterly direction, tracked northeast and then turned almost northerly. And that brought those strongest core of winds not only across the Channel Islands and northwest France, but also across southern and southeastern parts of the UK. And you can clearly see that in the gust data, which Mike Kendon came up with and published. So the gusts in the pink colour there are all over 80 knots. The left-hand side is Storm Ciarán and the right-hand side is the Great Storm of 87. Similar-ish values around northern France and the Channel Islands, slightly stronger in the 1987 event. But the key observation from this is if you look in the top of the images towards sort of south-central England, the south coast and the southeast, you'll see the gusts with Storm Ciarán were generally between 40 and 60 knots, whereas within the Great Storm, they were in the order of 90 to 100. So much less damage with Storm Ciarán for the southeast of England. So just to summarise, Storm Ciarán, yeah, it was an exceptionally powerful windstorm. We estimate that these things tend to happen once every 20 to 30 years. So you could argue we were due another one, given it had been 36 years since the Great Storm of 87. Winds peaked at 100 miles per hour with gusts in the storm, but that's outside of anything that happened in association with the tornado. And we saw widespread disruption across the island anyway, but especially so with that tornado where some of the damage was localized catastrophic with that T6. For Jersey, it was pretty comparable in many ways to 87. 87 was slightly stronger. But the key difference, Storm Ciarán was far more predictable in terms of the development of it. It had already matured into a well-developed system just to the west of the area, and then had a relatively predictable track, especially for the Channel Islands. And we've seen major improvements in modelling since 1987. I think the global model resolution used to be 90 Ks in those days. It's now 10 Ks, and we also have high resolution models of 1.5 Ks. So, yeah, we're much better able to predict these systems far in advance, and that enabled us to give 4 to 5 days notice of this storm, allowing the island to prepare. But the most notable difference between the storms was the convective nature of Storm Ciarán, and obviously that T6 severe tornado, which is very unique and rare in the British Isles tornado record and that of northwest France. So that's all I had. I'm going to stop sharing and come back to. There we go. Back onto the conference. Yeah.
Excellent. Really good summary. And as you mentioned, we have a special issue for the November issue of Weather on the Storm Ciarán. So multiple articles coming out, which I think you're involved in writing at least one of those articles. So yeah, really look forward to that. And those of you members will get Weather. Those of you who aren't, well, there's a good reason to become a member of the Royal Met Society just for that special issue. Great. So we've got time probably for one quick question for Matt. If you want to, please put it in the Q&A. If not, Matt can answer it in slower time. I hadn't quite registered, Matt, but today is the anniversary of the 1987 storm. Came through, what, 15?
Yes, indeed, yeah.
So, yeah, very timely to be doing a comparison. So, so I had one quick question, Matt, and I don't think it was touched on in the presentation, but I just wanted to know what the impact of the sea temps were around Jersey in, I guess, providing more instability ahead of the storm coming in. Do you think that played an important role here?
Possibly. Sea surface temperatures were very high at the back end of last kind of autumn, so that potentially could have played a part. But I think the significant driver for that severe convection, that supercell system and the tornado, was the very, very, very strong low-level shear. So the cape, the energy, the instability of the environment actually wasn't particularly high, and normally that would be higher in a warmer environment. This is a cold season storm. So it's mostly the drivers for the storm were mostly from this exceptionally strong low-level shear, which again, I think there's a paper about in the anniversary special. So it'll be packed full of really interesting science around this this storm.
Brilliant. Great, Matt. So there is a question from Robert, but I might get you to answer it in slower time. You might remember kind of what went out in the forecast with the sea states at the time. But yeah, if you can put that in the Q&A, that would be great. So I'm going to move on to our final speaker this afternoon. Delighted we have Mo Davies. So Mo currently leads the work at the UK Health Security Agency, working on surveillance for heat and cold-related mortality, with an aim of developing the evidence base for public health impacts to adverse weather events. So, Mo, we're going to look at, I guess, the impact on health during 2023 due to weather and climate. Over to you.
Absolutely, thank you. I will share my screen. Great, so thank you very much for having me. I'm Mo Davies from the UK Health Security Agency, and I'll be talking about heat-associated mortality in England in summer 2023. It's not all about the extremes. I'll start by giving a bit of background on the topic of weather and health at the UK Health Security Agency before talking about our estimates of heat-associated mortality for summer 2023 and putting these into context with other recent summers in England. So firstly, the UK HSA mission is to prepare for, prevent and respond to infectious diseases and environmental hazards as these can affect health. And within that, the Extreme Events and Health Protection Team, which is where I work, are the operational leads for the Adverse Weather and Health Plan for England. We run the Weather Health Alerting System in partnership with the Met Office, which can issue heat health alerts and cold health alerts. We provide guidance for the public and for professionals on protecting health from weather-related harm. And it's in our remit as well to build the evidence base on adverse weather and health. So what are the health effects of hot weather? This infographic summarises some of them. Some of the ones that might spring to mind, like heat exhaustion and heat stroke, are caused very directly by the heat. But it's quite rare for these to be life-threatening for large numbers of people in the UK. We don't really see the temperatures where heat stroke becomes a major threat to many people. We do see some of the mild effects that you see on the infographic, things like heat cramps or heat swelling, heat rashes, and really most of the mechanisms of heat effects on the body are to do with dehydration and to do with changes to blood flow in the body. And while these kind of mild effects can affect all of us, the main drivers of mortality are the knock-on effects of dehydration and changes to blood flow on the cardiovascular and respiratory system. These can trigger serious health events in people who might be vulnerable to them, things like heart attacks, strokes, and kidney failure. So in order to prepare for this, in partnership with the Met Office, UKHSA issues heat health alerts, and these provide early warning when adverse temperatures are likely to impact the health and well-being of the population. We moved in 2023 actually to an impact-based alerting system, which takes account of the forecast temperatures and the likely impacts on the health of the population, and it can consider a variety of meteorological and other factors that might influence the ultimate impacts. We can issue 3 different levels of alert: yellow, amber, and red, and you can see the matrix on the right-hand side here of how we assess the risk of a potential adverse weather event coming up based on the likelihood and the impact. A yellow alert would be for response, and that might be a low likelihood of severe impacts or a high likelihood of more mild health impacts. Those are targeted really at the health and social care sector to take action to protect those who are most vulnerable. Then an amber alert, which is for enhanced response, would be issued when there's a higher likelihood of severe impacts. And finally, a red alert for emergency response would be issued when there's a threat to life, even for those who are otherwise healthy. Since 2016, UKHSA and its predecessor organisation, Public Health England, have been publishing annual heat mortality monitoring reports. We do this because surveillance of mortality allows us to monitor the trends in a changing climate and understand the effectiveness of interventions we might put in place, like the Adverse Weather and Health Plan and the Weather Health Alerting System. We look at all-cause mortality because, as I said, the range of heat effects on health are quite wide. It could be a cardiovascular death or a respiratory death. It wouldn't be recorded with heat as the cause of death. So we have to look at all-cause mortality to detect these kinds of signals. I'll now talk specifically about our estimates of heat-associated mortality for summer 2023. For the purposes of our analysis, we define a heat episode as any day where an amber heat health alert was issued and in place for at least one region of England. They're issued at the regional level for the 9 regions, or that the mean central England temperature was at least 20 degrees, plus one day either side of any period that meets that definition. There were 5 heat episodes that occurred in summer 2023. I've got them in a table here. So the first one was quite early in the season in June. It lasted for a week, and it reached an amber alert level in several regions of England. This was followed by 3 much shorter alert periods, reaching only a yellow alert, but having the CET above 20 degrees, as you can see, which is why they count as heat episodes for our analysis. And finally, towards the end of the season, there was a very prolonged heat episode in September, which started off as a yellow alert, but it was then raised to an amber alert level as the temperatures remained high. To calculate heat-associated mortality for one of these heat episodes, we look at daily deaths during the heat episode, which we get from the Office for National Statistics, and we compare it to a baseline period. And what we use is the 2 weeks, 14 days before and after the heat episode. You can see that illustrated for just an example heat episode here, where it's lasting 7 days, and you can see that daily deaths have gone up during that period. And by comparing the average daily deaths in the heat episode with the 2 weeks either side, we can get an estimate of how much mortality happened due to the heat event. So now looking at a real example, this is what happened in summer 2023, looking at the 65 plus age group specifically. There's a lot going on this chart, so don't worry, I will talk through it. So we've got dates from May to September along the bottom there, and you can see that the 5 heat episodes I mentioned are the shaded grey columns that you can see. You can see the central England temperature, which is the red line towards the bottom of the chart, and you can see how that's gone up in each heat episode. And then at the top, you can see the black line is daily deaths. You can see that it fluctuates as random variation day to day, which you'd expect, but there are also spikes specifically during each of the heat episodes that we looked at. And if you can make out the green horizontal line, that's the average, as I was just saying, of the 2 weeks before and after each heat episode. So you can see that aside from all the random variation, there is a spike above the general average level during the heat episodes. You might see if you look at any of our older reports, we used to compare to a baseline of the previous 5 years rather than comparing to 2 weeks before and after, but because of the impact of the COVID-19 pandemic, it's not really reliable anymore to look at the last 5 years in that way. So that's why we've switched to using a method that looks at the 2 weeks during the summer. So using this method, we calculated that there were 2,295 heat-associated deaths in England in summer 2023. This was mostly in older age groups. So in the 65 plus age group, there were over 2,000 deaths, which accounts for most of them. That's to be expected because a lot of the factors that make someone more vulnerable to heat, like having a pre-existing cardiovascular or respiratory condition, are more prevalent in that older age group. We also looked for the first time this year at heat-associated deaths between genders. We found that it was actually close to equal between men and women, so just over 1,000 in each of those groups. Next, we looked at heat-associated mortality by region of England. We do this adjusted per million population. And out of the 9 regions, we found that the southeast of England had the highest rate of heat-associated deaths per million population at 50, and lower rates were seen in the east of England and in London. London often has a very high raw number of heat-associated deaths, but that's partly due to the larger population in London. And in fact, the rate is quite low compared to other regions of England, which might be to do with this isn't age adjusted. So London in general will have a younger population and then fewer people who are particularly vulnerable to the effects of heat. Looking finally at heat-associated mortality by heat episode, you can see here again the 5 heat episodes that I mentioned, coloured for the amber ones at the beginning and end of the season and the yellow ones in the middle. And on this chart, it's the total area of those bars that you see, which represents the volume of deaths that occurred in that time period. But from the height, you can see the intensity of the impact. So while that heat alert towards the end of the season in September had the most volume of deaths over that longer period, it was actually the one before that in August which had the highest heat-associated deaths per day. That was only a yellow heat health alert that was issued, so that really emphasises for us that although there might not be a risk to the wider population in a yellow heat health alert, there is absolutely a risk for those who are most vulnerable, and that's why public health action is needed in response to the yellow health alerts to protect people who are vulnerable. So now come on to talking about how we can put these numbers into context. As I said, we've been issuing these reports on heat mortality since 2016, so we now have a reasonable time series of the estimates we have for each year. You can see on this chart that the blue bars there, 2023 was the 3rd highest number of heat-associated deaths since reporting began, and it also had the 3rd highest number of heat episode days, which is the red line that you can see. And while it is changing a bit from year to year, there's a general trend of increasing heat-associated deaths, and that's to do with the increasing temperatures that we're seeing, and also partly to do with the growing and aging population that we have, which means there are more people who are vulnerable to the effects of heat. Another way that we can put these numbers into context is by comparing the observed heat-associated deaths we see with a statistical model that we run, which estimates how many deaths would have been expected in each heat episode based on historic temperature mortality relationships in England. We do this modelling at a regional level, looking at the last 5 summers, and the model takes account of the effect of temperature in the last 5 years on mortality immediately on the day and also at a short lag. And it also takes account of things like weekday effects, general, seasonal and long-term trends in mortality. This slide shows what we found comparing the observed estimates and the modelled predictions for summer 2023. You've got each of the 5 heat episodes and also the overall numbers at the bottom. And for each one, you've got modelled on the top compared with observed. Overall, if you look at the all 5 heat episodes together, the modelled estimate was extremely close to the observed estimate for 2023. So that indicates that the deaths we saw in 2023 were broadly in line with what we would have expected from the relationship in the last 5 years. You can see, though, there are some differences for individual heat episodes. So if you look at episode 4, which is the one in August that I mentioned had the very high sort of intensity of impact, that observed number of deaths is higher than what the model predicted. And one of the reasons that we do this is to identify maybe factors aside from the temperature that might be causing higher deaths. And that will inform future decisions about issuing alerts and what level of alert should be issued. One other thing to highlight is we also did this modelling in 2022. And in that year, the observed deaths overall were much lower than predicted by modelling. The main reason for that was that there was a difference in heat episode 2 for that year, which was the period in July 2022 from the 10th to 25th, during which we saw the first 40-degree temperatures. And it was also the first ever level 3 heat health alert that was issued. That's what's now called a red alert, but at the time it was called a level 3. There was a huge level of media attention on that alert and a huge level of public awareness. And while we can't be sure, we can speculate that maybe the action that was taken by the public and by professionals, the emergency response community, because of that, led to the deaths that were observed being lower than the deaths that were predicted by a model for that period. So some key takeaways: summer 2023, even though it didn't have the temperature extremes that we saw in 2022, still saw the third highest number of heat-associated deaths since reporting began. We had significant deaths even during the yellow heat health alert periods, which shows that we do need public health action to protect people who are vulnerable to heat, even when those yellow alerts are issued. And the mortality surveillance and the comparison with the model mortality that we do will inform the continuous improvement of the weather health alerting system and provide evidence for action in future adverse weather events. Thank you for listening. Happy to take any questions.
Brilliant. Thanks, Mo. Yeah, if you have any questions, please put them in the Q&A. Thanks to Nevin, who's put a link to an article which may be of interest linked to this. So thanks for that. While I'm waiting for questions, I had a couple actually, Mo. So obviously it's really good to see the breakdown both of age and gender and kind of by region. Have you looked in more detail at things like the impact within comparison between cities and rural areas or coastal and non-coastal areas? And have you noticed a difference there?
That's a great question. Yeah, we are often asked if we can look. Currently, the numbers that we look at are just at that regional level, and apart from London being more urban than the other regions, there's not much that you can see. But we're definitely interested in looking at smaller regions, particularly that there's an urban heat island effect that can occur where temperatures within cities can be higher than you'd expect from the areas around it, and people are interested in understanding that for different cities. It's something we are keen to do. It does become, because it's estimated based on something that naturally varies anyway, you can see that the confidence intervals already are quite wide, and as we get to smaller and smaller areas, we would have less confidence about which areas are really more at risk than others. But it is something we want to look at, and we're specifically going to address it in the next report we publish on 2024, what level of breakdown we can do.
Brilliant, thanks. So question in the Q&A, is there a linear relationship between temperature and the health effects of mortality, I guess, in this situation, or is it more an exponential relationship, or what kind of relationship is that?
Yes, I think epidemiological research tends to find that a linear relationship is not a very good way of modelling it. So one reason for that is that obviously if you're looking at temperature as a whole, then there are effects at very cold temperatures and at very hot temperatures, so that's already not linear. But we do model it using a cubic spline, so that's a way of modelling a non-linear relationship between temperature and mortality, where exactly the effects get more and more extreme as the temperature increases.
Right. So Len, it's more of a comment. I think clearly meteorology dominates for a given event. The size of the surge is of utmost importance. I guess to kind of follow on from that, really, do you have a feel for the impact of these heat health alerts? So we know the numbers of deaths during a period when there's an alert out, but do you have a feel for if there was no alert, actually, there would have been a higher number of deaths, therefore, we're having a real positive impact by putting these alerts out?
Yeah, it's a difficult one, because obviously it wouldn't be ethical to not issue an alert and see what happens. So we can't do things like that, but there is an ongoing evaluation of the adverse weather and health plan, including the alerting system, which is aiming to look at that with a logic model, and we may be able to model what might have happened without the system, but it's a tricky one because we can't know.
And a question from Ken. Obviously, we focused on heat for this presentation. Is there a trend for cold mortality? And if there is, are you able to share something in the Q&A, a link to something for a bit further reading, if possible?
Yes, definitely can share some links. The HEC report that's already been mentioned has some analysis of cold mortality as well. We don't have anything similar in terms of an annual report on it. Cold mortality is a lot more difficult to estimate because the effects are lagged over a much longer period. So it can be 2 to 4 weeks after the actual cold day that the effects of that are seen in mortality, and that makes it quite difficult to produce an easy to understand estimate. But that is something that I'm working on currently, is coming up with a methodology so that we can begin reporting annually on cold as well, and monitor that as the cold days change in the future.
Great, thanks, Mo. So I'm going to close off the meeting. So if you could put a link in the Q&A against Ken's, and there also is a question, final question from Gerald. So if you get a chance to answer that before we close off, that would be fab, Mo. But yes, I've got a couple of slides just to close, really just to say a thank you for everybody attending. Hope you found that a really interesting meeting. We hope to run these events annually. Again, the State of the UK Climate Report comes out each year at the end of July, and it would be good to have a meeting to kind of take a closer look at the report and aspects around the report. Just for information as well, we have 2 events running next week that you may be interested in. The first one is our Diverse Voices series. So we're doing a Celebrating Black History Month next week on Tuesday. If you're interested, it's a virtual meeting, so please do register to join. And the second one is the Masterclass series. So the second in this series, oops, disappeared, is running next Wednesday afternoon. Again, a virtual meeting be hosted on Zoom, and this is looking at data assimilation in forecasting and reanalysis. It keeps appearing and disappearing, but there we go. So yeah, just a big thank you from me to Mike, Judith, Joanne, Matt, and Joe. I hope you enjoyed the event, and yeah, see you soon.